Shall we start? Is it okay? So my name is Laurent, and here is Antoine. We are working in the Toolchain working group, Toolchain team. I'm more working on CI side, and Antoine is more working on LLVM side. We will be presenting some benchmark results. The presentation is quite short, and do not hesitate to cut and to ask questions in the middle. And what else? First, I want to say that the benchmark we are presenting are coming from the data we are presenting are coming from the CI we are running. So first, I want to say a few words about the CI. The Toolchain CI I am using is okay. Let me. So the purpose of the CI is to update all the toolchain, all the components at the same time, and to regularly run a full toolchain benchmark. We are building all the components, benchmark on different benchmark. I will describe afterwards, and check against a reference to see if there's any regression. These steps are done regularly every few days, and if there's no regression, we are not going further. We are storing the baseline reference, and it takes few hours of benchmarking to do that. If we detect a regression, we will be trying to reduce this regression to a single component and a single commit. That will take more time to process, and by doing this, we can reduce and have a very precise report, a very precise benchmarking report on the single commit. Once we have the single commit regression, we are reporting it and storing in Jira card and so on. So this is the principle of the CI we are working, and the role of the CI is first to early track and report any regression. It was not designed to follow and to display a detailed report of the benchmark. So just to say, the purpose of the CI was to early track and report any regression, any precise regression. And we are using this data for this presentation. So as I was quickly saying in the first slide, when there's no regression, the CPU time used is really small. And when there's a regression, we are using more CPU time. And this is useful for having a very, very precise report. So thanks to this, we are able to have a different flavor of this benchmark. We are tracking the GNU and LLVM toolchain, different tests, on various, on all the architecture, different boards. There are some I didn't rate, different options and so on. We are tracking the code size and execution time, and also some numbers around the vectorized loop. And all these data are tracked, and we are looking for any regression on the whole benchmark, but also on every individual function. We are getting the size, for instance, of any individual functions. And if the function is growing significantly, we are detecting, and it can be reported in the same way, more or less, with different thresholds and so on. So one more word about this. This approach, the big advantage of this approach is to have the ability to have a very a precise report down to a single commit, and also at the same time not using much, a lot of CPU time. So well, that's the framework we are using. To report the data, we are storing them on LNT, and we are using the LNT as a dashboard, and this allows us to see the trend and also the details of what we want. All the data we are computing are stored on the LLT. This is one of the view LNT allows us. This could be a daily report that could be used, but there are many other view that could be useful on LLT. Did I forget something? Okay. Then on LLT we are we are reporting code size and code speed, and this is the data we were using, and Antoine will be presenting.
Okay. So before looking at the actual benchmarking results and graphics, there are just a few small explanations about how to read the graphs on the next slides of this presentation. So on the right, you can see that the x-axis shows the execution time, and the lower is faster there. And on the other dimension, the y-axis shows text size, and then lower is smaller there. The objective is obviously to be smaller and faster than the reference. So the most interesting points will be on the bottom left corner. And the opposite points on the top right corner are bigger and slower than the reference. In this slide and on the remaining of the presentation, the reference is always GCC02. The compilers used for benchmarking were built from GCC and LLVM main branches from April 2024. It's not possible to give a single revision, or the different configurations are run separately from the other and at a different time. So different revision could be used. For example, GCC02 could be run 2 days before GCC03, and then being 2 days older than this one. Arch64 target were used for every compilation with no additional compilation flags. The run were done on TX1 machine, which is a Cortex A57. Sorry. So spec CPU 2017 benchmark was used for for this results. We looked only at the C and C++ application, so there are no Fortran results here. I think it will be the purpose of another presentation later today. Again, no run were done specifically for this presentation. Everything was extracted from existing CI results, which can be found in the TCWG Jenkins page, and also in the results repository and on the LNT dashboard, like Laurent said on the previous slide. So, okay, let's start with code speed optimization levels, so O2 and O3 for both GCC and LLVM compilers. So what can we see here? First, GCC O3 is the fastest configuration. It's almost a bit more than 5% faster than GCC O2 when you compute the geometric mean of every performance variation, so on all spec benchmarks. It's also bit more than 20% bigger. In this case, that does not really matter, as O3 is meant to be speed at all cost. Next, GCC O2 is the smallest and the slowest configuration. LLVM O2 can be seen as an interesting trade-off between GCC O3 and GCC O2. And on the opposite, LLVM O3 seems not very interesting compared to LLVM O2, as it's more than 5% bigger without providing any speed up. We can even think that it's a bit slower than LLVM O2. I think it's hard to say that because the execution time difference is probably in the noise range, which is about 0.35% on average in this presentation. Okay. Next, let's look at the code size optimization level. So OS and OZ still for both GCC and LLVM compilers. So GCC O2 is the fastest and biggest configuration. It's expected, as O2 is not a code size optimization level. The smallest configuration is GCC OS. LLVM OS can be seen as an interesting trade-off, as it provides almost half of the code size reduction for just a third of the slowdown. LLVM OZ on its side seems not very interesting compared to GCC OS because it's bigger and slower, but it's still interesting if we look only at the LLVM configuration. And even if it's just maybe 7% code size reduction at the cost of more than 10% slowdown, it's still interesting, as OZ is size at all cost. So it's nice to have this configuration when you use only LLVM. Now, let's add link time optimization to the previously seen configuration. So link time optimization configuration are displayed using star symbols here. So first, we can look at the two most remarkable configuration, which are GCC OS LTO, which is the smallest configuration overall, and also LLVM O3 LTO, which is the fastest configuration. There are two interesting trade-offs, in my opinion. So that's LLVM O2 LTO and LLVM OS LTO. LLVM OS LTO is nearly 40% smaller than GCC O2 with no slowdown. There are two interesting things to observe here, in my opinion. The first one is that LTO is here always beneficial. I mean that on code size optimization level using LTO always provide a code size reduction, and on speed optimization level using LTO always provide a speed up. The other interesting thing is that performance on size variation seems to be almost always the same for each compiler. So for example, when you look at GCO3 and GCO3 LTO, the vector is quite similar as when you look at GCO2 and GCO2 LTO and GCOS and GCOS LTO. So when you use GCC, using LTO almost always provide a very small speed up and something like a 20% code size reduction. It's quite the same for LLVM with a bigger speed up, maybe 5%, and except for LLVM OZID, where there is no speed up, but 5% slowdown. Again, OZID is not meant for speed, so that does not really matter. It could be interesting to look at it, though, maybe it's just to understand what happens there. Okay, for LTO. So here, that's just previously shown configurations in a bigger graph. So every configuration that we run in the CI, in the benchmarking CPU 2017 code speed configuration are shown here. Again, nothing was run for the purpose of this presentation only. All results were used from the existing CI results. Okay. Okay. Before finishing, two last graphs which are here to illustrate that benchmarking results evolved over the time and over the release. So here on the left, you can see the results for three configurations, so GCO3, LLVM02, and LLVM03. So that's the 100 last run for every of these configuration. And on the right, you can see the evolution, so size and time for one of these configuration. So for example, you can see that the last GCO3 points are almost the smaller and the slowest one, so they are probably displayed in this area. It's also interesting to see that because it shows that results presented previously could have been a bit different if extracted at another time. Okay, so I think that's it for this presentation. So we saw that Linaro's CI benchmarking results can be used to compare compilers' configuration. We looked at a few comparisons of such configurations, so comparing different compiler and optimization levels. So we saw that on spec 2017 C++ benchmarks for ARCH64, LTO is always beneficial. GCO3 and O2 are the fastest and smallest configuration, and LLVM almost always provides interesting speed size trade-off. So I think that's it for this presentation. Thanks for listening, and if there's any question, we'll be happy to try to answer them.
Okay, just a quick one. You're looking at size and execution speed. Have you also looked at compile times?
Good question, and I got the remark several times already. That will be indeed very interesting to look at that. For example, to get the cost of using LTO. Yeah, that will be a nice addition to to that. For now, we don't have the figures to do that, but yeah, that's a possibility.
Because we actually want, as compiler engineers, to compare apples to apples. And if LLVM's 02 is taking more time to compile as GCC's 03, then it would be a fair comparison to compare performance you get for the compilation resource you put into getting that performance. That will be definitely a part of a future version of this presentation.
So have you looked at any profile guided optimization? So you can apply 03 to the hot path and only do 02 to the stuff that's only going to be infrequently executed.
Sorry.
So do you do profile guided optimization at all?
Yeah, okay. No, unfortunately. I did that separately just on just a single LLVM configuration, but that's not done as far as I know for now in the Linaro CI, but that should be also very interesting. I know that profile guided optimization combines quite well with link time optimization. I mean, the benefits could almost be directly aided. So yeah, that will be nice to do that, I think. Yeah.
Yeah. So there's a trade-off with how many extra instructions you generate for stuff that's only in the hot path.
No, that will be surely the best results overall, both in terms of code size and execution time. I'm sure about that.
When you do regression tracking in creating a JIRA, do you do that as soon as it's a bit less than before, or is there some?
Well, there's a threshold starting from which we are considering as a regression, and the threshold is we are computing a noise that is we're computing a noise all across the benchmark to see if the board we're using is if the results are stable or not. And starting from the noise, we are detecting, we determine the threshold starting from where we consider it as a regression. As Antoine said, on this on the whole benchmark, the noise was about 0.3%, and we usually use 2 sigma or 3 sigma to consider it as a regression. Maxime, do you want to add something about? Okay. Thank you.
I have another question, but I forgot already.
Okay.
Okay. Thanks a lot.
Thank you.